In this video, we're going to focus on the topic of Newton's laws of motion. Let's directly begin with the first law. The first law states that a body at rest wants to stay at rest unless acted upon by a force. Now, what does that mean? In Newtonian mechanics, if a body or a system it has zero velocity or it is moving with a constant velocity, these two states are meant to be equal to each other. And the reason for that being, it can be described by using relative frames, because for the frame to us, yes, this body is at rest. But also, for the frame of reference of this system, it is also at rest, and everything else is moving. The only time the body isn't at rest is if it's acted upon by a force, meaning that it is accelerated in some fashion. In the most intuitive sense, a force can be a push. It basically describes a change in the condition of the system with this famous formula, F equals ma. We know what A represents, it's acceleration. What is m? M is called mass, and a lot of people don't understand this. It's distinctive from weight, and we'll get to that later. But mass is not exactly how much something there is, because in some cases there might be a little of something, but it still might have more mass than another thing which has many. That was a stupid sentence, but I feel like you get the idea. Mass is basically resistant to the change of state or the change of velocity in our body or in our system. That is why it is inversely proportional to the acceleration. And force defines this relationship between mass and acceleration. It is easy to see that if you have a body with a smaller mass, then you don't have to apply much of a force to accelerate it, let's say by c. But if you have a body with a greater mass, then you need to apply a greater force to accelerating it by c. That is the simple relationship. And like acceleration, force is also a vector quantity, and its unit is defined as newtons, which is equal to kilograms times meter per second squared, because mass is defined in SI units with kilograms and acceleration with meters per second squared. We already know that. The third and last law of motion in Newtonian mechanics is that for every action there is an opposing reaction, meaning that for any kind of force that you apply to a body, you will feel the same force in the opposing direction. That is why when you try to push anything, it feels like that the thing you're trying to push is also trying to push you. But you shouldn't see this as if these two forces are going to cancel each other out. That's a common mistake. These two forces don't cancel each other out because, well, that would be kind of paradoxical, isn't it? this opposing force is born from the action of this force. It purely exists because this exists. You can imagine them as if they were two separate things from each other, and they're not acting on each other as if they were just two different independent vectors that you can add up. These are linked with each other in such a way that they can't really cancel each other. If that was the case, applying a force from the beginning wouldn't be impossible, because for every force you apply, the opposing force would cancel, and zero force is the resulting. Now again, by coming to the previous topic that I stated, that weight is not the same thing as mass, because weight is a force and mass is, well, mass. It's a quantity of its own. What we call weight on Earth is basically the resulting force of our mass with the gravitational constant of Earth. That is why for every different planet, your weight would be different. On the moon, you'd weigh much less, but you'd still have the same mass. Another thing is that we can calculate the gravitational constant of 10 meters per second squared, which is actually not really close to the actual value. That would be 9.81 meters per second squared, from the equation of Newton's law of gravitation. I'm not going to get into proving it because it's a nasty one, but it looks something like this. The force of gravity to both sides, which only makes sense if you have two different bodies and these forces would be equal to each other, just in different directions, is equal to g, our constant, times the mass of these two different bodies divided by the distance squared between them. And this is called the inverse square law, and it will come up in many different places in physics. This is just one example. So if we want to calculate our gravitational constant from this, well, let's say the mass of our Earth is m, and we want to calculate this for a body standing on Earth with the mass of m. Then we'll say that since we know that Fg can be described as m times g, which is our gravitational constant that we want to calculate, is equal to our constant g times the mass of Earth, the mass of our body, divided by Earth's radius. I won't get into the calculation of it, but if you look at the numerical values online, you will get the exact result of, well, maybe not exact, but pretty close to 9.81 meters per second squared. Because obviously that this is just an approximation for many different distances on Earth, and it would be changing just slightly if you tweak with this radius value.